Okay. So for this next talk, we got Nigel Brown. He's going to be bringing the heat with some knowledge, not just about developer tools, but also bringing a bunch of context. You should listen to Nigel. He knows about community. He knows about development. He's going to be breaking down the landscape of developer tools in the container ecosystem for us with an introduction to developers for containers. Break it down.
What's up, everybody, and welcome to a developer's introduction to containers. My name is Nigel, and I'm going to be your guide on this journey. I'm a community manager here at VMware, and I love containers and all of the ecosystem that has grown around them. And the reason that this talk came about is because we spend a lot of time talking about cloud-native technologies and all of the other technologies that are built around it, like Kubernetes and orchestrators and Docker, but there hasn't been a lot of approachable overviews to what containers are and where they came from. This talk is an attempt to explain containers and the underlying technology without any hand waving. So consider an alternate title, everything you wanted to know about how containers work but didn't want to ask. We're going to accomplish that with three outcomes. The first is that you'll understand what containers are and how they came onto the scene. The second is that you'll be able to containerize an application and run it locally. And the third is that you'll be able to deploy your container image to a remote registry. And if any of those words didn't make sense, by the end of the talk, they will. To complete the workshop portion, you'll need to have Docker installed on your machine, as well as an account on Docker Hub. And we're going to go into a little bit of background around containers. So if you want to get that stuff set up now, you'll have plenty of time and you'll be able to work through the demo at the same time that I'm doing it. So that brings us to our first part. What are containers and how did they get here? And instead of starting with containers, I want to start from processes. If you have access to a Linux shell or bash or something like that, you can type top into your terminal and see a list of processes that are running on your machine at any given time. So that we're working from a common definition, I'm going to borrow from Michael Karisk's The Linux Programming Interface, where it says that, put most simply, a process is an instance of an executing program. Processes are the entities among which the kernel must share the various resources of the computer. And if there are two words that I want you to remember whenever you think of container, it is process isolation. A container is a process or group of processes running in isolation. When you type top into your machine, you'll see that there are perhaps dozens of processes that are all working around in the same space. They can all see each other and know what's going on. But when we containerize an application, that process that we create only sees what's relevant to it. As far as it knows, it has an empty instance of an operating system and its own playground within which to do its own work, which is great for security, for portability, for speed, because all that's running in the container, all that's running and all that can see the process are exactly what it needs to be able to work. So the way that we achieve this process isolation is by leveraging several features of the Linux kernel. We're going to talk about two of them. And those two features are namespaces and C groups. Now, from the man page for namespaces, it says that a namespace wraps global system resources in an abstraction that makes it appear to the process within the namespace that they have their own instance of the resource. A metaphor I like for this concept are apartments in an apartment building. Utilities come into the apartment building, but it appears to each apartment that they have their own instance. In our use case, utilities represent resources like network or the process ID counter and more. So when you're looking inside a top, you'll see that every process has a number associated with it, and process 0 and 1 are typically reserved for what it takes to initialize our operating system or boot up. And when you look in a container, you'll see that typically your application is running with process ID 1. That's a whole instance of the process ID counter that's working inside of the container, that is different from what's happening outside. And that's achieved by having a separate namespace from within which to work. The second feature of the Linux kernel that I wanted to cover was control groups, or C groups. And from their man page, it says that control groups, usually referred to as C groups, are a Linux feature which allow processes to be organized into hierarchical groups whose usage of various types of resources can be then limited and monitored. So one of the uses of C groups is assigning a maximum number of resources each group can allocate to ensure that your critical system processes always have the resources they need to run. So that's the what of what containers are. And again, if there are only two words that you take away from this, they should be process isolation. That's what containers are. They're a way for us to take the processes that we are running on our machine and isolate them so that they're running in an extremely portable version of an operating system with only access to the files and libraries that it needs to run. So the how. Containers aren't a particularly new technology, even though they may seem that way. It seems like one day we're deploying to bare metal or mainframes or VMs, and then all of a sudden everyone's like Docker and containers and Kubernetes. This is how we're deploying. But it really was a long process to get to where we are now. And the technology that containers fall under is something called operating system level virtualization. It's highly probable that you're already familiar with a different form of this type of virtualization, but we're going to touch on some of the more notable points. One of them is back in 1982 with the creation of Unix. Unix has a feature called chroot, which allows us to change the root directory. And the effect that that has is isolation, because if you turn a different directory into root and then install into it all of the files that it needs to see, we give the impression that we have a separate operating system or this isolation from the host operating system that we've been running in before. It's rarely the best choice for security reasons, but the first major point that we have for commercial adoption of what came to be known as containerization is back in 2000 with Virtuoso. The next point that I like to bring up is with Solaris, this concept of zones, because it's the point at which the term container started being used in like the marketing materials around Solaris zones. And the widespread adoption anecdotally, and the first interaction with containers that most people I talk to have is with Linux containers, or LXC, in 2008. So that's still over 10 years ago. When Docker came onto the scene in 2013, they weren't creating a new technology per se. They were making it easier and more secure to leverage containers for today's workloads. In fact, Docker's initial releases used LXC before they wrote their own implementation of it. It was Docker's ease of use, their strategic partnerships, and the suite of software tools that came up around them that made them why their name is synonymous with containers today, and why they were able to get widespread adoption in the industry. So the software that Docker created to interact with the Linux kernel was packaged into a library called libcontainer. For standardization and to further encourage the development of containerization technology, Docker donated libcontainer to the Cloud Native Computing Foundation to start the Open Container Initiative. The OCI used Docker's donation to provide two specifications: the runtime specification and the image specification. They further used libcontainer to create runc, which is a reference lightweight runtime built from the specification. A more fully featured reference container runtime is provided by the Containerd project from CNCF, and Docker's engine currently uses both of those projects. So now we've covered what containers are and how they got here. They didn't just appear overnight, even though it felt like it. There's been a lot of development in between 1982 with Unix and chroot to now us spinning up Docker containers and deploying them to Kubernetes. The second part of this workshop is containerizing an application and running it locally. I want to share with you all a GitHub repository that we're going to be working from. So the repository is at github.com/pnbrown /containers-intro. So again, that's github.com/pnbrown /containers-intro. And if you start at the top, you'll see a lot of the information that I just covered in a much more easy to digest format. And what we see down on part 2 is containerizing an application and running it locally. So in this section, we'll create a minimal Python application to demonstrate how to containerize an application. It's written by my friend Mofi, and it greets a website visitor by name and then provides them a quote of the day. After containerizing, you're strongly encouraged to customize the application. You'll see neither Mofi or I are front-end web developers, and the application is a very true reflection of that. And so I encourage you to take what we have here and create it into your own thing. So the first step is to clone the repository, of course. So I'm going to go ahead and do that here. And then I'm going to change into that directory. And we'll look and see what's inside of it. So we chose Python as an accessible language for participants. There are 4 files that comprise the application. We've got a hello.py, we've got a quotes.txt, a requirements.txt, and a templates view.html, which contain our web server, our list of quotes, dependency, and the web page, respectively. When a user visits our site at the root URL, they'll see text defined in our hello.py server. If they append hello/their name, they'll get to the page defined in the templates view.html, which will show them a random quote from quotes.txt. So if you have a local Python 3 installation and want to run the application before containerizing, you can follow these steps to do so. So the first thing that we want to do is install our dependencies, which in this case is just Flask. I'm going to do pip 3 here because I'm running Python 3 and okay, Flask is installed. And then I'm going to run Python 3 hello dot. Okay, so if I now go and look on port 80, we should see our application. So the front page that we get to is Nigel's container intro workshop, pinned hello/your name to the URL. And here in all of its beauty is our website. Hello, Nigel. If you look at what you have in life, you'll always have more. If you look at what you don't have in life, you'll never have enough. Quote there from Confucius. Yeah, that's what the application looks like. And we're running this application right now just on our local machine. It's not isolated in any way. And what we're going to do next is to take this application that you've now seen running locally and put it into a container and run that isolated version of the application. So the next section is about writing the Docker file. And in the world of containers, it's helpful to know the difference between a container, an image, and a registry. We mentioned earlier that a container is a process, a group of processes running in isolation that are running in isolation. But what about processes when they're not running? So containers are built from a set of instructions. Commonly, the instructions are contained in a text file called a Docker file. And from these instructions are built an image. Images are stored in registries until they're ready to be run. You can think of an image as a recipe and the required ingredients, and the container as our cooked meal, while registries would be the cookbooks in which we keep our recipes. So now we're going to gather our ingredients and write a recipe. What we have in the top level directory is an empty Docker file. There's also a directory called safety, which has the completed Docker file and the original implementation of the view.html page. In case you decide to customize and break something, we have all the safeties there that you can just copy over and work from if you need to. So we're going to start editing the Docker file in our root directory. So container images are created in modular layers. Generally, each line in a Docker file creates a new layer that builds upon the one immediately preceding it. The unique hash for each layer is then calculated and cataloged. In practice, this speeds up subsequent container builds because the modular layers contained in our images are reused whenever possible. This means that the first builds will generally take some time, but each subsequent build completes much faster. Further, you should ensure that the lines of the Docker file most likely to change are toward the bottom to ensure speedy builds. Docker will only rebuild the image from the line that changed to the end of the file. So let's have a look at our Docker file. The first line of our Docker file defines a base image. So this is the operating system that we're going to use to run our application in. I'm going to be using Buster. And so we have this from line, and this is an image that's provided from Python and their slim version of the Buster operating system. So we're going to do from Python and pull in this slim Buster image. The second line creates and sets our working directory for the image and for any of the subsequent adding, copying, or running of files. So we just want to set our work directory to /app. The next thing that we'll do is copy our requirements into our working directory. Remember, when we ran the application locally, we ran that requirements.txt file and installed in the requirements for the application. So we're going to copy that in now from our top level directory that we're currently in into that app directory that we're working from inside of our container. The fourth line, installs our dependencies that Python will need. By using the image the Python organization created, we can ensure that everything Python, the language, needs to run is already a part of our image. And now we're just going to install the dependencies that we need. The fifth line copies the rest of our current directory into the working directory so we can access all of our files once the container is running. So remember, we still had that, the view.html page, we still had all of the quotes. We need all of the rest of that stuff to come into our directory, or into our app directory. So we're going to copy everything there. The sixth line indicates on which ports Docker should listen when our application is running. Our Flask app runs on port 80, so we'll expose that. The seventh line determines the entry point for the running container. After the container is built, it runs the entry point command. Ours will be Python. The interesting thing about entry points and this next part, command, is that the entry point is encoded into our image, and the command line can be overwritten by changing an argument when we run the container. So if we build this and we decide, instead of running the hello.py file that it sees in its current directory, we want it to run some other Python file, this container is a valid working Python image. We could just, instead of saying, run our container, we add an argument at the end of that for a different valid Python file that would then run inside of our container. So that eighth line sets the command that's provided to the entry point. For our purposes, we want to run that hello.py file that we copied over. Okay. So that gives us our Docker file that we need for this demo. In case something went wrong, you can copy and paste this in. And we also have the safety directory as well that has the completed Docker file in it. So now we want to build our Docker image. We wrote the recipe for our container, and now we need to assemble the ingredients through the building of the container image. The Docker engine will go line by line of our Docker file and assemble it. If you have an account on Docker Hub, please use that when you name your image. You should use the tag for version control. Use whatever versioning or tag makes sense for you. So I'm going to start running this command now. So we have docker build -t for tag. My username is pnbrown, and we'll call this container, say, container intro at Spring. It's a very long name. Name yours something shorter. And then we'll have a colon and then a tag at the end. We'll call this 1.0. And this is the part that I always forget. Remember to add this period at the end because it shows you it says build from this directory. So the directory that we're currently in, which is the containers intro directory, we want to build. Okay. That went really quickly because I rehearsed this ahead of time, but for you all, it may take a little bit longer. And so what we want to do now is to run our image locally. So we need to map the port that we exposed in our Docker file to one that's not currently in use by our system. I like 4567 because it's easy enough for me to type. And that's reflected in the command below. So the -p handles our port mapping in the form from our host port to our container port. Additionally, you can use the -d flag to run the container in the background or in detached mode. So I'm going to show you that container running now. So we want to do docker run -p 4567 to port 80 pnbrown /containers container -intro -at -spring. Okay. Unable to find it locally. I typed something wrong. Container intro at Spring 1.0. There we go. So now if we go look on localhost port 80, we don't see anything on port 80. And that's because we're mapping port 80 in the container to port 4567 on our host machine. So instead, I'm going to now try to go to localhost 4567 and we see our application. And I'm going to do what we did again, /hello Nigel. And if we refresh the page, we can get other quotes and you can see the logs happening inside of our container. Now we have it running, we have our container running. Now, if we quit the container, what happens? Refresh the page, we get nothing. So that shows you that our container is running and serving our website with the port mapping. And as soon as the container stops, then we lose the site. So the last thing that we want to do is deploy our image to a remote registry. So we built the container, we built the image, it gets stored in the local container registry on our machine. You can see all the images currently in our local registry with the Docker images command. Some recipes are too good to keep to ourselves, like this one that we just made here together. We can share it by publishing it to a remote registry. For our use case, we'll share it to Docker Hub, but there are many other registries that are out there and available for you. We refer to putting our images in repositories as pushing them. Once you log into your Docker account, which I've already done, you can then push your image to your repository. Once it's there, anyone can pull your image into their local registry to run it. So I'm going to run this Docker, I'm going to run Docker, Docker run, Docker push, pnbrown /container -intro -at -spring 1.0. Okay. And that pushes it up to Docker Hub. So any of you who are watching can now go and pull this image by running the Docker run command that we had before. That brings us to the end of this demonstration. Hopefully we've accomplished the 3 goals that we had set at the beginning. So now you have a better understanding for what containers are and how they came onto the scene. You can containerize an application and run it locally, albeit a simple Flask application, but there are tutorials out there for anything that you want to containerize. And you are able to deploy your container image to a remote registry. Thank you so much for joining me here on this journey to introduce you to containers. And we'll see you around. Take care, y'all.
Docker build, Docker push, Docker run. Thank you, Nigel, for giving us that awesome rundown and live demo. If you want to talk and ask more questions, I can see that the Slack channel for this talk is already pretty poppin'. Get in there. It is session, a developer's introduction to containers. There's a Zoom link in there where you can follow up with some cool Q&A. Thanks again.